introduction to the compressible flow. So first definition, compressibility. So this, see this picture. So if you compress the volume, that is, if you apply the pressure to this volume, the volume will decrease. Okay, simply it is a compressibility. I apply the pressure, the volume will decrease. So it has the compressibility. So the exact definition is a fractional change in volume dV by V per unit change in pressure. By applying the pressure, how much volume is decreased. Okay, so this is the definition of compressibility, and we are not denoting using this tau for compressibility. Is it clear? And if I rearrange, I will get 1 by V into dV by dP. Then I'm adding one minus sign because the volume is decreasing. So tau is equal to minus 1 by V dV by dP, and this V is the mass specific volume. It is not the velocity, it is the volume. So normal volume formula, it is mass divided by density. Here we are assuming it is a unit mass. So it is the mass specific volume. So it is 1 by rho. Okay. So first definition. So fractional change in volume per unit change in pressure. Then Mach number relation, Mach number definition already you studied. Simply the ratio of speed of an object by speed of the sound. So V by A. And in aerodynamics 1, so we dealt with low speed, that is less than 0.3. So we assumed it is incompressible. But in AD2, that is compressible aerodynamics, we will deal with high speed, mainly supersonic flow. 1 is greater than 1. So this we are considering as compressible flow. But generally air is the compressible flow, whether it is less than 0.3 or greater than 0.3, air is the compressible one. But just for the simplification of theory, we are assuming less than 0.3 is incompressible. The decision is made based on this experimental graph. So the graph is drawn between density ratio and the Mach number. Here that rho naught is the initial density and rho is the final density. So this shows the ratio of initial and final density. So they got this type of graph for density ratio. So they found up to certain Mach number, the variation in this final to initial is just 5%. Okay, after that it drastically increasing, and they found this Mach number is 0.3. So for simplification, they assumed they neglected this 5% change and they assume the flow is incompressible, just to simplify the procedure. After that, they consider this as compressible flow. That's why in aerodynamics 1, even though the air is compressible, we consider everything is incompressible because the speed is falls less than 0.3. Is 10. So if you are interested to find the properties of this gas, whether it is compressed, they expand, how the properties are changing, then this is our system. Okay. So any part in the universe over which we are interested. Okay, that is called system. And anything around the system is called surrounding. And two types of system. In thermodynamics, mostly you study the closed system, mainly this piston, that type of system only you studied. So here there is no mass in, mass out. Okay, there is no air flow or gas flow in and out. So this is the closed system. Here only energy transfer will be possible. See here, if I heat, there will be a increase in internal energy. Okay, only energy transfer can take place. There is no mass exchange. So this is the closed system. Then open system. So whatever you studied in fluid dynamics and aerodynamics, flow over the aerofoil, flow through pipe, etc. and all, it has the mass in, mass out. Okay, this is the open system. In AD2 also it will be open system. So the open system, another name we are calling as control volume. Okay, so there will be a mass in and mass out that we are calling as control volume. And that control volume, further it has two types. One is Eulerian, another one is Lagrangian. In that we will mostly use this Eulerian. So the difference is, assume this is one flow field, and here this dashed line shows the control volume. So here the control volume is fixed and air comes in and goes out. Okay, so this type of control volume only we will consider for AD1, AD2 and all. This is mostly used Eulerian. And Lagrangian, see here n number of control volume they were given. So here the control volume moves along with the flow. So this is another type, but there is no scope. Mostly we'll use this Eulerian. So in this AD2 also, all the derivation, it will start with this control volume. Then we apply the three main equations: continuity, momentum, energy. From that only we will derive all the properties. Okay. So the control volume is very important in this AD2. Then state, just explains the property of the system. What is the pressure, temperature, density of the system? That is called state. Then two types of properties. It's also already you studied: intensive, extensive. So example of intensive, okay, the pressure. So I'm taking two cubical box. So each box has 1 bar pressure. And if I join or merge two boxes, still it will be 1 bar only. Okay, the pressure will not increase. For example, in your home, you may have n number of rooms. Each room has the same atmospheric pressure only, right? 1 bar, 1 bar. If I remove the walls, it won't be 4 bar. Still it will be 1 bar only. So this pressure will not change, depends upon the mass. So this type of property is called intensive. And extensive. So instead of pressure, if I take energy, for example, joule. Okay. So again, I have two cubical box, each has 1 joule, 1 joule. And if I merge these two boxes, then I will have 2 joules. Okay. So this energy, mass, volume, enthalpy, everything is a mass dependent. If I increase the mass, that amount also will increase. So this is called extensive. This you studied in thermodynamics. So these are some basic definition. Then next, okay, some the laws of thermodynamics. So zeroth law, if two systems are in thermal equilibrium with the third one, then all three in thermal equilibrium with each other. This is a 0th law. And first law, it shows the conservation of energy, and this is the equation. So we can take this example. So here I'm heating it. Okay, I'm heating this system. So I'm applying the Q. Because of this heating, the internal energy of the gas is increasing. So E is increasing so that the gas expands and pushes this piston upward. So there is a work done, that is W. Okay, so I'm heating this system. So I'm adding the Q so that the gas internal energy is increasing, E is increasing, so that it expands and pushes this piston upward. So this Q is now converted into this E and W. So if I write, it will be Q is equal to E plus W. And here they are rearranged. Q minus W is equal to E. So this is the first law of thermodynamics. The second law of thermodynamics is very simple. Always heat flow from hot body to cold body. Example, they mentioned this hot coffee. So if you keep the hot coffee in normal air, normal room temperature, so there will be a heat transfer. So the coffee becomes cold. Then perfect gas. So it is an imaginary substance. There is no perfect gas in real condition, perfect gas or ideal gas. So we imagined one gas, and that should follow this formula: P is equal to rho RT. Okay, but mostly all the light gases like oxygen, nitrogen, air, etc., everything can be properties can be calculated using this perfect gas calculation. But the heavy gases like refrigerant, water vapor, and all cannot be included within that. So that calculation will not be correct. But all other gases, the properties can be calculated using this perfect gas assembly. So P is equal to rho RT. And these are some basic values and equation that you studied in thermodynamics. R is the gas constant. So specific gas constant is equal to universal gas constant divided by molar mass. And so this R, you can find it for any gas. So here I found it for air. So universal gas constant is 8.314 joule per mole Kelvin. and molar mass of the air is 28.8. This value may be a little bit vary, the difference upon the books. So from that we found R value is 288.7. Mostly in the book they will use, I think, 287, right? So 287 joule per kilogram Kelvin, R value. And specific heat definition, you know, right? So amount of energy required to raise the temperature of unit mass by 1 degree. And this is the specific heat ratio, small gamma, which is the ratio of Cp by Cv. So Cp is specific heat at constant pressure, Cv is specific heat at constant volume, and this is the relation between Cp and R, gas constant and specific heat at constant pressure and volume. So R is equal to Cp minus Cv. And this is the Cp-Cv formula. This also you studied. Gamma divided by gamma minus 1. This is R divided by gamma minus 1. You know, for air, this gamma is 1.4. And in propulsion, you might have studied for gas also. Mostly they will take gamma is 1.3. So for air, if you substitute 1.4, so here they got 1010, but mostly we will take 1005 for Cp and 717 for Cv. Okay, so these values also will be used for the calculation. Cp is 1005, Cv is 717, and these are all the remaining basic equations. So this is the enthalpy equation. So enthalpy is equal to internal energy plus work done, pressure into mass specific volume, and E is equal to CVT, internal energy, enthalpy is equal to CPT. These formulas also you studied. Then next, in the perfect gas, again we have two types, calorically perfect, thermally perfect. So in aerodynamics, so whatever we used, mostly it will be a calorically perfect gas because the temperature will be less than 1000 Kelvin. So in that case, the Cp, Cv values are constant, 1005. If we are taking air, Cp is 1005, Cv is 717. Then second one is thermally perfect, where the temperature is more than 1000 Kelvin. Maybe in hypersonic or in the propulsion, the combustion gases and all, if you take, the temperature will be more than 1000 Kelvin. In that case, you should not take the constant value because Cp, Cv will change depends upon the temperature. Okay, and next one is different processes. So first one is adiabatic. Definition, you know, so no heat is taken away from the system, but important one is the condition is T0 is constant. Okay, stagnation temperature is constant. This is very important. This you might have not studied in that thermodynamics, but throughout this AD2 we will use these conditions. Okay, so for adiabatic process there is no heat added or taken, so T0 is constant. Another one process I missed, that is isothermal. There static temperature is constant. Okay, we won't use the isothermal. So the isothermal means static temperature is constant. Adiabatic means T0 is constant. Then reversible process. So the process can be reversed without leaving any trace to the surrounding. So here P0 is constant. Okay, and isentropic definition, you know, if the process is both adiabatic and reversible, then it is called isentropic. And condition is T0 is constant, P0 is constant. Then only the process is isentropic. Okay, so these two terms are very important. And yeah, enthalpy equation just now I told. So enthalpy is the total energy. Okay, this is internal energy, and this is the work done, the pressure energy. And entropy also you studied, ds equal to d cube by t, change in temperature by original temperature. And this entropy is the loss of energy. So this is the total energy, enthalpy, and this entropy is the loss of energy which is not available for the useful work. But you might have studied this definition. So measure of disorder or randomness in the system. It's simply a loss of energy. So don't forget, this is very important conditions. Okay, adiabatic T0 is constant, reversible P0 is constant, isentropic T0 and P0 both are constant. So throughout this calculation, we will use this condition. Okay, so up to that, the basic definitions are over. Now this is the wave propagation. If you take the flow field, so there will be n number of fluid particles, right? So due to the movement, so all the particles will be disturbed. So this disturbed fluid particles will emit the sound pressure waves. Okay, so in the flow field, infinite number of fluid particles will be there. Due to the movement of the particle, it got disturbed, so it is emitting the pressure waves continuously. And you know the speed of the pressure waves, sound waves, a sonic speed. Okay, A. So here we are discussing the wave emitted by this single fluid particle. In the book, they are calling this disturbed fluid particle as point disturbance. So here we are discussing the point disturbance at different speed. Here it is at rest. Here it is moving at subsonic speed. Here the point disturbance is moving at sonic speed. In the fourth one, it is moving at supersonic speed. So in the first case, so the disturbed particle is at rest and it is continuously emitting the pressure waves. So at last we see, if you see, we are getting the concentric circles. So this is the first case. If the point disturbance is at rest, then second case, so the point is moving at subsonic speed. That's why I mentioned A by 2. A is sonic, it's just half of the velocity, and also it emits the pressure waves. So due to the movement, so we are not getting the concentric circles. We are getting the circles like this. So due to the movement, so all the wave fronts are moving to the right hand side. Here the particle is moving to the right hand side. So the wave fronts also moving to the right hand side. So wave front mean, for example, this is the pressure wave emitted by the particle and it is moving to the right hand side. Then this portion is the wave front. Okay. So all the wave fronts are moving to the right hand side here because the particle velocity is subsonic, A by 2, and wave velocity is A. So the wave moves first in the subsonic case. Then in sonic, both particle and its emitting wave moving in the same speed. So this is the particle moves with the sonic speed. Also it emits the pressure waves. So both has the same velocity. So both coincides at one point and it moves. This is for sonic case. So zero velocity, then subsonic, then third one is sonic, then fourth one is supersonic. So here that fluid element velocity is 2a, so twice the sonic speed. So here what happened? So the point disturbance velocity is 2a and it emits the pressure waves, which velocity is a. So after few seconds, if you see the pressure distribution, that is wave distribution, it will be like this. Okay, so the point moves first because of supersonic speed and waves comes next because of the sonic speed. So this will be like a cone-like structure. This is the difference. So in the subsonic, so the wave velocity is high, so first it moves, but in the supersonic, the point velocity is high, so first the point goes. After that only the waves will come. So this is subsonic case. So these are all the pressure waves, sound waves, right? So in the subsonic case, even if I stand so in front of the aircraft also, I can hear the sound because the pressure waves are coming first, the sound waves are coming first. So I can hear some aircraft is coming if it is a subsonic case. In the sonic case, I can hear only if I exactly come just above me, then only I can hear the aircraft is coming. But in the supersonic, if I stand here, even if I stand here, I cannot hear anything. I cannot sense one supersonic aircraft is coming. Only I can sense if it crosses me. Then only I will fall within this sound wave region. Okay. So in the subsonic, before coming itself, we can identify. So there are some sounds, so some aircraft is coming. If it goes in sonic, once it comes about to me, then only I can recognize. But in the supersonic, after crossing only I can identify because the pressure waves or sound waves are coming behind. So this is the idea. And here we are dealing with the supersonic flow. So I'm taking only this last case, supersonic speed. So instead of the point, here they have taken the aircraft and it emits the pressure waves, which forms one cone-like region. So this cone is called Mach cone. Okay, in 3D it is called Mach cone, and 2D if you take these lines which is drawn tangential to this all these circles is called Mach line or Mach wave. Okay, Mach line or Mach wave in 2D. So as I said, if you stand here, you can't hear anything. Only if you come within this what is that pressure wave region, then only you can hear it. So they are calling this outside region is zone of silence, and inside region where you can hear that disturbance is called zone of action. Okay, so outside the Mach cone it is zone of silence. We cannot hear anything. Only inside the cone we can hear the disturbed pressure waves. So that is called zone of action. This they may ask in 2 marks sometime. With this diagram you have to explain. Then, so this angle they are calling as Mach wave angle, mu. Okay, so in the bottom I explain how to find that mu. Same condition I am taking here. So initially, okay, you can take this as disturbed particle or aircraft, it's up to you. So I'm taking one disturbed particle which is moving with a supersonic speed. V is equal to 2a, for example, you can take, because simply now you take the velocity is v and it emits the pressure waves with a velocity a. Okay, so the point velocity is v and it emits the pressure waves with a wave velocity a. After t second, I am checking how where it moves, how the pressure waves are formed. So I found this particle A is moved from A to B after t second, and the pressure waves move from here to here. So I know the velocity of particle and wave, also the time second. Using that I can find the distance traveled. Okay, so from A to B, the distance traveled is Vt, velocity in the time, and for this wave, the distance traveled is At. Okay, so point velocity is V, wave velocity is A. After t second, I can find where it moves. Also the distance I can find it, Vt and At. So I know the distance Vt, At. Now I am taking the Mach line. So Mach line is nothing but a tangential line drawn to the circles. Okay, like this, it will be extended further. Then I am drawing one perpendicular line from the Mach line to this, the initial point of the point disturbance. Okay, 90 degree. Now it forms one right angle triangle. So this angle is mu. So this distance I know At, this distance is Vt. Now if I write sine mu, it will be At by Vt. Tt get cancelled, so it is actually it should be a caps V. Okay, it's a velocity. Mistakenly typed small v. So A by V, that will be equal to 1 by m. So the Mach wave formula is sine mu is equal to 1 by m. This all. Then continuation to this wave propagation, we are going to see how the streamline patterns are formed for subsonic and supersonic flow. Okay, so first I am taking the subsonic flow. So in the flow field, I am keeping one cylinder here. Okay, so this is the final result. If I keep the cylinder, we will get this type of flow pattern. Last time itself you studied. So in the flow field, as I mentioned, there will be n number of fluid particles. So here I mentioned only one fluid particles, which is moving at subsonic speed, and the emitted waves moves at the sonic speed. So always wave will move first. Okay, this is the particle and it emits the waves like this. So here what happened? So the waves are first hitting the object. Okay, this is the cylinder. So waves are moving first. So the waves first hit the object and it will be reflected back. Okay. So the waves are hitting the object and it is reflected back. So depends upon these disturbed waves, this particle adjusts its path and flows smoothly over the object. Okay. So in the flow field, before the particles, first wave hit the object and the reflected waves and these upcoming waves both collide and create some disturbance. Depends upon the disturbance. So this sense some object is there. So depends upon the disturbance, it adjusts its path and flows smoothly over the object. That's why in the subsonic flow, whether it is airfoil or any object, we will get these smooth lines. Okay, is it clear? So first waves hissed and reflected back. So due to the disturbance created by the reflected waves, the particles adjust its path. It won't go straight. It adjusts and moves smoothly over the object. This is what happened in the subsonic. But if you take the supersonic, so here I have taken supersonic flow where m is greater than 1. For example, I have taken one rectangular bar. Here also n number of particles should be there. I am taking only one particle and you know the wave pattern. So the particle is moving with supersonic and waves are moving with sonic. So first the particle will go. So here first the particle will hit the surface and it will be reflected back. Okay. For example, here I have taken particle velocity is 3. It hits the surface and it is reflected back. So due to the hit and impingement, there will be a loss in kinetic energy. So initially the Mach number is 3. Due to the impingement, it loses some kinetic energy. So the Mach number is reduced to 2 now. The blue color line. Assume this blue color is the reflected particle. So here I have taken only one particles, but in the flow field, n number of particles will be there. Okay. So n number of particles coming with a Mach number 3 and this reflected particles coming with a Mach number 2. So what will happen? These reflected particles cannot move upward because this particle velocity is very high. So both collides at certain distance from the object and forms the thin layer that is called shock. So I will repeat if you want. So in a supersonic flow, this is the flow structure. So particle moves first, then waves comes behind it. So particle first hit the surface and it is reflected back. So due to the impingement, there will be a loss in kinetic energy. So the reflected particles has the Mach number of 2, but the upcoming particle has the Mach number of 3. So this Mach number 2 reflected particles cannot move upward because this particle has higher velocity. So both collide and forms the thin region, and that region is called shock. And depends upon this object, the shock wave structure also will vary. And the thickness of the shock is around 10 power minus 5 centimeter. And depends upon the object, we will get different shock wave pattern. See here we have the slender body with a sharp edge nose. So here we are getting attached oblique shock wave. So here we are getting attached oblique shock wave. And if this is the blunt nose, then we are getting the bow shock. Okay, so this type of shock is called oblique. And this is called bow. Actually, bow shock is the combination of all normal and oblique shock wave, I will tell you. For example, if you see this region alone, it's almost straight. Okay, if it is straight, then it is called normal shock. And if you see this region, it is inclined. So this is called oblique shock. After that, what will happen? The strength will decrease and finally it will vanish. And this is called Mach wave. Okay, so the bow shock is the combination of different shocks. Center region is normal shock. and this inclined is the oblique shock. After that, the strength decreases, finally it will vanish. This is called Mach wave. So we have three basic equations. I know that: continuity, momentum, energy. So in this area 2, for all the derivation, as I said, first we will form the control volume, then we will apply the three equation: continuity, momentum, and energy. Okay. So after applying these three, then we will derive the other properties. This is the procedure for all the derivation. Control volume, then these three basic equations. So continuity equation, you know that simply mass flow is equal to rho AV, which is constant for all the stations. But the important thing is, it's not simply rho AV, it is rho AVN. That means that velocity should be normal to the area. Okay, for example, this is station 1, this is station 2 in the control volume. So here I have taken only one normal flow conditions. Assume here it has tangential velocity also W1. So normal velocity is V1, tangential velocity is W1. And if they asking the continuity equation for both direction, so what are the direction? It will be only one equation, that is rho 1 A1 V1. You should not write rho 1 A1 W1, because W is not perpendicular to this area. Only this V1 is perpendicular to the area. So whatever the direction, continuity equation will be rho A Vn. So it should be rho A V1. Okay. Momentum equation just starts with Newton's second law. F is equal to ma, and you know that A we can write it as dv by dt. Then dt, if you take it here, that is m by dt into dv. This m by dt is nothing but m dot mass flow rate, and dv I can write it as, that is, if you apply to this control volume, it will be v2 minus v1, and m dot also I can multiply inside, m2 v2 minus m dot 1 v1, and force I can write it in terms of pressure. Force is equal to pressure into area. And again apply this to this control volume, station 1 and 2. It will be P1A minus P2A, and mass flow rate at the station 2 is rho 2A2 V2. Mass flow rate in the station 1 is rho 1 A1 V1. Even though it is same, simply they are given like that. Then rearrange, finally you will get this equation. P plus rho V square is equal to constant. Okay, start from Newton's second law. Simply we have to apply this to this control volume, pressure into area, and this mass flow rate. So the general equation is P plus rho V square is equal to constant is the momentum equation. And then the last time you studied P plus half rho V square is equal to constant. What is that? This P plus half rho V square is the Bernoulli's. It is applicable only to the incompressible. Okay, so please forget this Bernoulli. So many times I have seen your previous section also. So they used to confuse with this Bernoulli and momentum. Instead of momentum, they used to write this Bernoulli equation. So the momentum equation is P plus rho V square is equal to constant. Okay, this is applicable to both incompressible, compressible. But this Bernoulli has a limitation. It is only to the incompressible. This is not the momentum equation. It just relates pressure and velocity. It is totally different. So forget that Bernoulli. So continuity, momentum, finally energy equation. This also you studied, that H plus V square by 2 is equal to constant. Again, I'll explain once again. So again, I start with the first law of thermodynamics. dq minus dw is equal to du. So first this dq. So in this control volume, initially there is no heat transfer. It is 0. Assume I am applying one heat transfer. The value is q. So dq will be q minus 0. Sorry, q. Okay. So instead of dq, I am going to write q. Then dw, it's just a pressure work. It will be P2 V2 minus P1 V1. So this is the pressure into volume, okay, not the velocity. So pressure work done is pressure into volume. So if you apply this PV to these two stations, station 1 and 2, it will be P2 V2 minus P1 V1. But here we need the minus sign. So here we have the minus sign. So if you put minus sign here, it will be minus dW is equal to P1 V1 minus P2 V2. So this term also I found it. So dQ I found, dW I found, then energy. So the total energy is equal to internal energy plus kinetic energy. You know, kinetic energy is half mv squared, but here we are taking mass specific, unit mass. Okay, that's why it is not there. It is 1. So it is E plus V square by 2. Again, if you apply that, to these two stations, it will be E2 plus V2 square by 2 minus E1 plus V1 square by 2. So now I have equation for 3 terms. Now substitute. So instead of dq, it is q. Instead of minus dw, it is this term. Instead of du, I have this term. Then rearrange. Simply I am taking E1 and E2 to the left hand side. Then I can get P1 E1 plus E1, which is equal to enthalpy H1, and this is equal to enthalpy H2. That's it. Then rearrange, we will get Q plus H plus V square by 2 is equal to constant. Okay. Q plus H plus V square by 2 is equal to constant. This is the general energy equation. But if you take isentropic or adiabatic, the condition is T0 is equal to constant. That is, there is no heat addition or rejection. In that case, this Q will be 0. You will get only H plus V square by 2 is equal to constant for isentropic and adiabatic. So mostly we will use this equation. Only in the Rayleigh flow, we will take this Q where we are dealing with the heat transfer. So the general equation is H plus V square by 2. Equation is rho A Vn is equal to constant. Momentum equation is P plus rho V square is equal to constant. Energy is H plus V square by 2 is equal to constant. That's it. So next one is speed of sound derivation. First we will start with the control volume. Then I will apply continuity momentum equation. Then we will come to the final equation. Here, before starting this control volume, we will explain how to get this pressure wave, sonic disturbed wave. So here I am taking piston with a stationary air filled it. So the velocity is 0 and pressure is atmospheric pressure and temperature density. Okay. So piston filled with the stationary air. So velocity is 0. Now I'm pushing the piston with the velocity dV. Okay. So what will happen? It will compress the air next to it. Initially it is just stationary. Because of this movement, it compresses the air just next to it. So the pressure and density is little bit increased. dP, d rho little bit increased. And if you continuously move this piston to the left hand side, you can see one moving pressure wave. Okay. And if you stop moving the piston, this wave will disappear. If you want to get this wave, pressure wave, you have to continuously move the piston so that you can get one pressure wave which is moving at the sonic speed. And this side we have the stationary air. So this is the physical setup to create the pressure wave. We got the pressure wave. From the setup, we are drawing the control volume. So in the station 1, we have the stationary air, velocity is 0, P rho we have, pressure density. And this side, we have the air velocity dV, because air also moving right here. So air velocity dV and pressure density it is given P plus dP, rho plus dP. And also in between, we have the moving pressure wave with a velocity sonic speed. And then the next step is we have to apply continuity momentum energy. But all the derivations it is possible only if the object is stationary in the real time also. So in the sky, aircraft is moving, right? So air is stationary, it is still, only the aircraft is moving. But how we are assuming the aircraft is still, the air is moving, relative wind we are taking. Okay, so the object should be stationary, then only we can apply all the theoretical thing and find the properties. So here also, this moving wave, we cannot apply all the equations and all. So we have to make this moving wave as the stationary. So I'm imagine another one control volume. So there I am taking another one flow which is opposite to this original flow condition with the velocity A. So here it is the moving wave in the real condition, but I don't want this moving wave. I need the stationary wave. So practically it is not possible, because if I stop moving the piston, it will vanish. So to apply the theoretical condition, I imagine another one. What is it? Imaginary control volume. There I am assuming another one flow in the opposite flow direction with a velocity A. So if I superimpose this to the existing control volume, now instead of 0, I have the velocity A, and this A equals, so that the wave velocity is 0 here, and behind that again the velocity is changed. Now it is A minus dV. Okay, so this is the original control volume, but it is of no use. So this is the imaginary control volume, just to apply the conditions. So where I superimpose with imaginary flow with the velocity A get cancelled. Okay, thank you. So the wave is stationary. The same thing I mentioned here. So in the station 1, I have a velocity A, P rho. Station 2, these are all the conditions with the stationary wave. Now we can apply continuity and momentum. So here see the area is constant. Okay, so it is simply rho V is equal to constant. And if you apply this equation to this control volume, it is simply rho A is equal to rho plus d rho into A minus dV. Both sides we are applying it. Then if you simplify, we can cancel this rho A, and this one, it is a very small term because dV is very small, dP is again small. If you multiply further, it will be very small. So we are cancelling this dV by dP just for the simplification. So we have remaining only this term. And if you rearrange this for dV, actually this is a capital V. Okay, it's a velocity. Okay, this is a dV. It's not the mass specific volume, it is the velocity. So I am writing the dV equation, which is equal to A into d rho by rho. This is one equation. I got it from the continuity. Okay, so simply I am applying rho V to station 1 and 2. It's very simple. Then rearrange. Then momentum equation. You know, it is simply F is equal to m dot dV. dV is V2 minus V1. And F, I can write it as pressure into area. So apply to both station. So here P into A, here P plus dP into A. Okay, this is F. And m dot, you can take it at any station because it is constant. So I'm taking in the station 1 because it is simple. So density, area, and velocity A. Then V2 minus V1. Okay, this is V2, this is V1. This, if you simplify, we will get this final one. Again, if I write it for dV, I will get dP by rho A. I got two dV equations. Now I'm going to equate these two dV equation. So dV is equal to, from continuity, it is A d rho by rho. From momentum, it is dP by rho A. So if I equate these two, the density I can cancel. Remaining you will get A square is equal to dP by d rho. But what we need, A square is equal to gamma RT. So I have to convert this P and rho in terms of gamma RT. So to introduce this gamma term, I'm going to use isentropic relation, and for this RT, I'm going to use ideal gas law. Okay, using these two equations, I'm going to convert this P and rho in terms of gamma RT. So first, I'm taking isentropic relation, the relation between pressure and density. So the simplified form is this caps P. So P divided by rho power gamma is equal to constant. And if you rearrange, you will get P is equal to rho power gamma C. So we need dP by d rho. So I'm going to differentiate this with respect to density. Okay. So this is the same equation. If you differentiate this with respect to density, so this is constant. Just I'm writing it. And this rho power gamma, it is like x power n. So if you differentiate, you will get n into x power n minus 1. Okay. Then instead of this C, I'm going to substitute this P divided by rho power gamma. This just I'm keeping it. Okay. So instead of C, I'm substituting P divided by rho power gamma. Then this term, same term, I'm just keeping it. Then this rho power gamma minus 1, I can rewrite like this. That is rho power gamma divided by rho. Okay. So now I can simplify rho power gamma. You will get only gamma P by rho. So further I have to convert this P by rho into RT. I can use simple ideal gas law. So P by rho is equal to RT. Substitute. So instead of this, I'm getting gamma RT. So dP by d rho is A square. So A square is equal to gamma RT. And A means it is simply root of gamma RT. In supersonic flow, mainly if you take external, always it will be accompanied with these shock waves in supersonic flow. So here we have 4 types of wave. First is Mach wave, second one is normal shock, third one is oblique shock, fourth one is expansion fan. Okay, and first one is Mach wave. This is very weak wave. Okay, so it will occur for the very low Mach number where m is approximately 1. So for the low Mach number, we will get this Mach wave. It's simply like a pressure wave, so it's just a weak wave. So across the wave, there won't be any change in properties or change in flow direction. Simply it will appear, that's it. It won't affect the flow property. And the angle, just now we found it, minimum mu, maximum it goes to 90. Okay, this is the first wave. Very weak wave, just a pressure wave. It won't affect the properties and all. Simply it will appear. And these two are the strong compression wave. Okay, normal shock wave, oblique shock wave, strong compression wave. So it will compress the flow. So this will convert high Mach number to the low Mach number. So it will reduce the decelerate the flow. So once the Mach number velocity decreases, all the pressure, temperature, density will increase. And the last one is the expansion wave, just opposite to the compression wave. Expansion, Mach number will increase behind the wave, and pressure, temperature, density, everything will decrease. This is the general idea about these types of waves. Further, we'll explain what is this. So wait for a few seconds, some disturbance. Okay. So I said Mach wave is just very weak wave. So across the wave, there won't be any change in flow properties or flow direction. If Mach number is 1, here also it will be Mach number 1. If pressure is 2 bar, here also pressure will be 2 bar. It won't change anything. And then let me explain the normal shock, then you can come to this expansion fan. And these two are the shock waves, compression waves. First one is normal shock. Why this name comes means, always it will be normal to the flow direction. Okay, this is the flow direction. And the wave is normal to the flow direction. That's why this is called normal shock. And it is a strong compression wave. The strength is very high. So the compression rate also very high. So this converts supersonic flow to subsonic. So upstream of the flow, the Mach number will be supersonic, for example 3, and behind the wave the flow will be converted into subsonic, maybe 0.2, 0.3, 0.1, approximately I'm telling. So like that, it will convert supersonic flow to subsonic flow, and these changes occurs suddenly across this thin shock. Already I mentioned the thickness 10 power minus 5 centimeter. Okay, across this thin shock, there's a sudden change in property from supersonic to subsonic. Because of this sudden change, the process is irreversible. So the P naught is not constant. So experimentally also they verified. They measured the P naught 1 and P naught 2. They found P naught 2 is less. Okay, that is because of the sudden change in property across the waves. So the process is irreversible. P naught is not constant, but we are not adding or heating this we are heating or cooling the system. Okay, there is no heat addition, so the process is adiabatic, so temperature is constant, that is T naught is constant. So due to the sudden change in flow property, the process is irreversible, so there is a stagnation pressure loss, but we are not cooling or heating the system, so T naught is constant. Overall, if you see across the wave, this is a normal shock, across the wave the flow is non-isentropic. Okay, because T naught is constant, but P naught is not constant. If both are constant, then only it is isentropic. If any one is not constant, then it is non-isentropic. So across the flow is non-isentropic. Across the shock, the flow is non-isentropic. But in front of the shock, the flow is isentropic. Similarly, behind the shock, the flow is isentropic. For example, here I have P naught 1. The shock convert that into a P naught 2. This P naught 1 is constant within this region, in upstream region. So here the flow is upstream, that is isentropic, because P naught 1 is constant. Similarly, behind the shock, we are getting P naught 2, even though it is less compared to the P naught 1, but it is constant in this region. So here also flow is isentropic. Only across the shock, the flow is non-isentropic. Is that clear? So here P naught 1 is constant, so isentropic. So here P naught 2 is constant, so here also isentropic. But across the wave, there is a variation in P naught. Here we have P naught 1, here we have P naught 2. So across the wave alone, it is non-isentropic. Okay. And normal shock wave, it changes only the flow properties. Supersonic means it will convert into subsonic, but there is no change in flow direction. It is always straight. Okay, so there is no change in flow direction. Then next one, oblique shock wave. So this is also similar to the compression wave, but you see it is inclined. This is the flow direction, and it is inclined. This is the wave angle. It is not 90. So because of the inclination, the strength is little bit less compared to the normal shock wave. So this converts high supersonic to low supersonic. For example, this side you may have the Mach number 3, that will be converted to Mach number 2 or 1.5 something. Okay, it won't compress to the subsonic. Both sides it will be supersonic, but this side it will be high, this side it will be less. That's it. That's why the strength is little bit less, because it is inclined. So if this beta increases, shock strength also will increase, then Mach number also, the compression rate also will increase. Okay, this beta decides whether the shock is strong or weak. Okay, so it is 90 degree here it is less than 90 degree, so beta decreases, strength also decreases, compression rate also decreases. And here across the shock wave, again same conditions. Here isentropic, but across the wave it is non-isentropic because of the stagnation pressure loss. Here also we are not heating or cooling the system, so T naught is constant. And here properties changing, flow direction also changes. It is not parallel like the normal wave. Always the flow is deflected parallel to the wall behind the wave. So if you are keeping on ramp in the supersonic flow condition with the theta, there will be oblique shock wave from its nose, and this is the original flow direction. Always the oblique shock wave will deflect the flow parallel to this wall. if this is theta, then here also it will be theta. Always there will be a change in flow direction. This is the only difference between normal and oblique. Last one, expansion fan. It is opposite to the compression wave. It increases the Mach number. And see here, it is not the single wave. It has the n number of waves, weak waves. That's why this is called expansion fan. Okay, they used to call this as expansion fan because it has n number of waves. And if you see what is it waves, it is simply the weak Mach waves. Okay, the expansion fan contains n number of weak Mach waves. That's why they mentioned this is a collection of weak Mach waves. So I said across the Mach number, there is no change in flow property and direction, right? But actually, there is a small change in flow direction and flow property, which is negligible. Okay, the minute change in flow property and the flow direction, which is negligible. But here, in the expansion fan, we have infinite number of Mach waves. So each changes the flow property to the minute level. So as a bunch, if you see, there will be a noticeable change in flow direction and Mach waves, that is properties. Okay, as a single wave, the changes are not noticeable, but as a bunch, it changes the flow direction, also the flow property. And another thing, so sorry. So each wave, it changes the flow property and direction to the minute level I mentioned, right? So here there is no sudden change in flow properties. It is gradually changes across the infinite number of waves. So flow direction, if you see, it will be a little bit curved. It is not just straight. It will little bit curved. Then again, it will be parallel to this wall. So because of this gradual change in property, here the flow is isentropic. There is no stagnation pressure loss. Even though if it is there, it is negligible. Okay, so we are assuming the P naught is constant for the expansion fan. Is that clear?
Yes, sir.
Okay. And another thing, so this is the wall, and this is the supersonic flow, maybe Mach number 3, and actually it has to go straight, right? But see here there is a void, that means low pressure region. So this low pressure region sucks the flow, just flow above to that, so that the flow is deflected and it get accelerated. Okay, actually the Mach number 3 flow, for example, it should go straight, but because of this void, there is a low pressure region, so that sucks the upper flow, so that it is deflected and get accelerated because of the suction. That's why we are getting increase in Mach number behind the waves. And